苏菲还有他们走了，陈平他们走了啊？安慰一下啊。I think this one is a larger. Then I think this one might be okay. Is it okay? Okay. 张周没有来。Okay. Okay, some of you couldn't join us because of the big rain. So for this time, some of them will be joining online. And then we also got some visitors from SWE, the Thursday class. Okay. Any questions from last week? Tutorial lectures? I didn't go through the tutorials last week. Hopefully you have done it at home. And actually, I plan to discuss the exam this week, but we didn't manage to do it yesterday. So next week, we will discuss the exam, hopefully. Okay, next week. And then I'm not sure, maybe we can't do the quiz next week on time. So I'm not sure whether we want to postpone it or combine with the last quiz together. What do you think? Okay, combine. Okay, I'll consider combine. Okay, because we need to discuss quiz and then need to discuss test. So okay. Okay. Any other question? Any other questions? No? No? Okay. Want to warn you a bit. This week a bit involved. I cannot go too slow because otherwise later too drag too much. So this week a bit involved. So I beg your attendance this week. Otherwise you will get lost easily. There's some proof that I want to do. I want to let you see how the arguments go. They are just a simple argument that you could learn it. But okay, is it ready to start yet? Ready? Ready to start? Okay, ready to start? Okay. So last week we talked about locality on the graph. So we imagine ourselves standing on the vertex, and then we look at the neighborhood, and then we count the degree, and what else? We take operation between two graphs, okay, union of two graphs, looking at the subgraph, and then looking at type of graph. How is it a graph of bipartite? Can you partition vertex into two graphs? Is it okay or not? I think this one is the largest I can put. Otherwise, if I do full screen, it will become smaller. Unless you got some other tips. Okay. Which one better? Which one is better? You want first one or second one? First one? Yeah, if you got any idea, you can let me know. I don't know how to hide them. Can I hide them? I hide. I'm sure I'll hide. Okay. All right. Yeah. So today we will stand on the vertex and then we try walking on the ground. Okay. We try follow the edge and walk on the ground. Okay. So what do I mean by that? So first we will define one definition for the path. Is it okay? Is it large enough? Okay. So let's get an n and graph. Okay. So we want to walk on the graph. So what do I mean by walk on the graph? So a path of length n from one vertex u to the other vertex v in the graph is a sequence of graph edges. Okay, sequence of n edges. E1 up to En of G, okay, such that such that uh, such that the endpoints of these edges are precisely the vertex of the graph. So such that how to write? Okay, such that EI has the endpoint E sorry the let me see, let me think how to. Okay, so I plus 1 in. Okay, so for example, Maybe let me put example then. So you got V1, V2, V3, V4, V5, V6, V7, V8, V1, V2, V4, V5, V6, V7. Okay, so there's a path. So there's a path from V1 to V8. Okay, right. So the path is what? What's the path? So the path is E1, E2, E3, E4, E5, and then E6, E7. Okay, so the path is like this. Okay, make sense? Okay, so every okay, so when the graph is simple, so that maybe just some below. So when the graph is simple, do you remember what's the simple graph mean? The edge is directed or undirected? Undirected. Any multiple edges? No. Any loops? No. Okay. So no multiple edges, no loops. So when the graph is simple, then the path are the simple path. So we just need to write down the vertex sequence. So it's equivalent to write down the vertex sequence. So maybe x1 up to Sn plus 1. So for example, in this case here, we can write V1. Oh, I use V, is it? So maybe I use V. V. So V1, V2, V3, up to V8. So instead of specifying H, you can specify the point. Okay. So not that if you have something like this, then you cannot just specify V3 and V4, because I don't know whether you walk through the green one or you walk through the yellow one, right? But if it is simple, this case cannot happen. Okay. Okay. So okay, next. Okay, if what happened if this path go back to V1, okay, form a loop, okay, this we will call a circuit. So definition, the path is circuit if it begins and ends at the same vertex with length greater than 0. Okay. So first you have to walk and end at the same point, circuit. So form a circuit. And then length have to be more than 0. So you cannot say V1 is a circuit. Okay. So a path of 0 length is not a circuit. More than 1, more than 0, which is at least 1. So a loop is also a circuit. Okay. So loop, circuit. But circuit is not necessarily loop. Okay, because circuit can be longer. Make sense or not? Loops is circuit, but circuit is not necessarily a loop. Make sense? Okay. Next. So remark. So what's the path of the path of length 0? I repeat again, it consists of a vertex. It's called vertex, but okay. And then sometimes you will see that people use walk for path. Okay, so you walk around the graph, and a circuit will then be a closed walk. Are you okay or not? Yes. Closed walk. Okay, and then simple path. Okay. Simple path meaning there's no loop, so we'll call it a trail. Okay, so far so good. And try with this work out this definition for directed graph. Okay, so what I said just now are all for undirected graph. So try work it out for directed graph. So you can work only with the direction the same. Okay, so you cannot work like you cannot form a path using these two edges. Okay, so you can only just keep moving forward. So you can do E1, E2. So you can do E1, E2, but not E1. I think I wrote too small again. So let me try and move these things on. Stop. The dot dash. Okay. So need to make sure that the direction of the path is the same when you do directed graph. Okay. So you can work like this, but not like this. Okay. You can compose path when they have the same direction. Okay, so we have settled the path circuit. Okay, then we will place something later. Okay. But for now, you can imagine you walk through all the path in the graph. Okay. So we will define something called the is there anyone talking in the team? I see some. Okay. So one definition we can make is whether the graph is is connected or not. Okay. Are they connected? So meaning if the graph is connected, then that means for every 2 points, okay, there's this a path. We can meet every 2 points using the edge of the graph. Okay, every pair of distinct vertices. Okay, so if it is connected, that means every 2 points we can find a path. Okay, so if it is not connected, then we will call it disconnected. Otherwise, it is disconnected. So, okay, that one not important. So let me show you. Okay, let me let you see something. So for example, what is a connected graph? So a connected graph will be something like this. Okay. So every 2 points, there's a path. Every 2 points, there's a path. Every 2 points, there's a path. Okay, so this is connected. But something is not connected, for example, something like this. Okay. So this point is not connected to any other point. So you cannot walk to the edges. Okay. And then should we just straight away say, okay, maybe I straight away introduce this since I'm here. So for this part, this connected part, right, we will call the connected component. So in this case, there are two connected components. There's one connected component here. So if one thing is connected, then there's only one connected component. So let me make it precise here. So let me just throw this away. And so let me make this definition here. So what's the connected component? So connected component graph G is a connected subgraph of G that is not a proper subgraph of another connected subgraph of G. Okay. So if the connected subgraph is not part of the other connected subgraph, then they are different connected components. Okay. So should we see another example? Let me see this example. Let me bring this. Okay, so for example, this case here, we got these B, A, C are connected. Okay, D, E is connected, and F, G, H is connected. Okay, so these are three connected components. Okay, so simple idea. But later we're gonna use this. Okay. Okay, one theorem is I'm not going to prove this because there are more interesting theorems later. There is one simple path between every pair of distinct vertices of a connected graph. Okay. So what's the definition of connected again? So connected means so there's this a path between every pair. Okay, but here is stronger. There's this a single path. So the idea here is how to reduce the path into a simple path. So let's say you got, okay, maybe I just briefly tell some possible situation you will meet. So for example, you want to go from one point to the other point, right? So you walk, and then you maybe come across a circuit, and then you do like this, right? So this is not simple, right? Because there's a circuit. So what you do is you can remove this part here. Instead, you walk here. You can do this because it is connected. So I mean, if you want to go really detailed in, you should go and read the textbook. Yeah. So there's some technicality you need to take care. by removing this loop. Okay, so this is basically the idea. Okay, so far, okay, going okay. Yeah, so a bit fast, but I will slow down in the proof later. So I want to get through this definition first. Okay, so next part is about this bridge called the Königsberg Bridge. Okay, so in the old time, the mayor of the city. So the mayor of the city asked a question. Okay, so because this is the can I say that I think it's a center of trade, if not wrong, because every part here need to go through this center. Okay, so they built 7 bridges here. Okay, so the mayor asked, is there a path that passes through each edge exactly once? Okay, need to pass through every edge, but exactly one. Do you think it's possible? Exactly one without, yeah, exactly one. Is it possible? Do you think? Find a path that passes through each bridge exactly once. Okay, you can keep thinking it, but we want to introduce this notion is called the Euler path, because this question is solved by Euler, Leonhard Euler. So let's introduce this definition here. So you can keep thinking, but we will keep going. Then later we will see what's the answer for it. Our next part is called the Euler and Hamilton part. So let's deal with Euler first. Do you all know Euler? Euler number? No? He proved, I think it's he. Yeah, he proved that e to the I theta equal to -1. I think so. Euler. And then he get blind when he was old. And then even though he's blind, he still can write mathematics paper. He can still write paper. Crazy guy. Okay, so yeah, because he memorized everything in his mind. So even though he's blind, he still can calculate. Is there someone want to come in? Okay, so let us introduce us the Euler path. So one is Euler circuit. Okay, so circuit is a closed walk, right? I don't want to say loop, otherwise you confuse with the loop and the vortex. So an Euler circuit in the graph is first is a simple circuit that contains every edge. And then what is Euler path? Euler path also contain every edge of the graph, but you don't need to go back to the same starting point. Okay, so it's a simple every edge. Okay, so let's bring the example in. Okay, so we got two, one is undirected, one is directed. Okay, so does G1 has a Euler circuit? Can you draw an Euler circuit here? Okay, I'll let you think for a few minutes, maybe 2 minutes, and then see whether this graph have Euler circuit or Euler path. Try and draw. Just yeah, try and draw if you can. You can draw some circuit or path that contains every edge. And draw. Or you can discuss with your friend. Anyone draw a Euler circuit on G1? Anyone done? Anyone do a Euler circuit on G1? Anyone try? Anyone try? Okay. Draw an Euler circuit on G1. Where? From where? Yeah, G1. From which vertex? Start from which vertex? You can say ABC. Right? Draw 8. From where? From B to E, and then C, and then D, and then E. Okay, yeah, this work. And so this is the Euler circuit. Uh, G, you can show that there's no Euler circuit or Euler path. Okay. For this you need to check. But how about G3? G3, can you find Euler circuit or Euler path? G3. I guess there's no Euler circuit, but there's one Euler path. Who want to try? Euler path. Who want to try? Want to try? You want to try? Can you try? Start from where? Which vertex? Okay, AC and then E, and then A, B, D, E, and then B. EB, is it? C here, C here, C here. Okay, yeah. Okay, yeah, good. Uh, for H1, yeah. So H1, you cannot close it up because the direction is not right. So this one has no circuit. Okay. H2 got a Euler circuit. So, maybe one way is to start from A and then go up to B and then go to G, E, D, F, A. Okay. Contain every edge. How about H3? H3, you can do an Euler path. Okay, this one Euler path. This one Euler. Okay. Euler path. Euler. Okay. So we can't just like testing every graph like this, right? So we got a theorem. So how to find the Euler graph? How to see whether some graph has Euler graph or not? So there's one way, just looking at the vertex, the degree of the vertex. Yeah. So a connected multigraph. So that's mean the multiple edge along with at least two vertexes has an Euler circuit. Okay, this one is about circuit first. If and only if each of x vertexes has even degree. So if every degree of the vertex is even, then you can find a Euler circuit. Okay. So one direction is easier. Okay. So there's two directions, right? You have to prove that if you got an Euler circuit, then you count the degree of the vertex is even. If you start with even degree vertexes, then you can find an Euler circuit. So second direction is harder. The first one is easier. Why? Should I just draw it instead of write the whole paragraph? So Euler circuit implies degree of U is even for all U in G, for all vertexes U. Okay. So why is it true? Why is it true? So if you got an Euler circuit, then every vertexes have even degree. So you should imagine that you start with a vertex. Let me call it A. Okay. So this is the starting point. So maybe I write starting vertex. Okay. So you walk through a path, right? So you maybe pass by some vertexes, right? And then not that when you pass by the vertexes, right, you must go in and go out. Okay. So the degree of each vertex should be at least is 2. Okay, is 2 for the path. But you can imagine that maybe sometimes you will pass by this A again. Right? The Euler path maybe pass by A again. Okay, but when you pass by A, it adds degree 2 again. Okay. But in the end, it will come back to A because A is a this path is a Euler circuit. So the starting and ending vertex is the same. Okay. So when you go out +1, come in, you also ending you also +1. Right. And all the other place you just plus 2. Right. Okay, let me change the color. Changes of degree. So if you go here, you got a +1 here. But when you come back, you got +1 happen. And then at the other place, you got +2 distribution contribution from the path. Right. But since this is an Euler path, Euler circuit, so you only passes all the vertexes. Okay. So every time it passes through, it will add an even contribution. Okay. But at the original place, you have a +1 from the starting and then +1 from the ending. Okay. So altogether is even. And these are all the edges because of the definition of the Euler circuit. But to write out the whole paragraph, you should go and see the proof. I just give you the idea how to understand the proof. Okay. How about the other direction? Okay. So the other direction is harder. So if a degree, let me use this one. Let me use this cycle. So how on earth you can produce an Euler circuit even the degree is given? So if I tell you the degree is even, that means there are even paths coming up from the edges, the vertex. So how you produce the Euler circuit? Uh-huh. Uh-huh. Huh? Because the starting point also have 2 degrees. Yeah, but how you construct in general the Euler circuit? Yeah, true. This means you have a loop coming back. Okay, so in fact, given any connected graph, you can start from any point. Okay. So first thing, I just describe the procedure. Okay, first start from any point, any vertex, sorry, any vertex in G. Okay. And then 2 is you can form an I say Euler circuit. Okay, you can form a circuit. You can form a circuit. Form an Euler circuit. Form a circuit. Okay, form an Euler circuit. Euler circuit using even degree of vertexes. Okay. Yeah. So, but you run into a problem. For example, did I have an example? Okay, I did. So let me put an example here. So there are, for example, if we start with A, right? We can go from A to B to C to E to D to C to F to N. Then this is an Euler circuit, right? But I also can form an Euler circuit with A, B, C, F only. So maybe we can do. Maybe we can use this just this A, B, C, D, E. It's also a circuit, and then I also use up all the edges here. But in this case here, we can remove this part. Okay, we can remove this subgraph. We're left with another connected subgraph, and then we build the Euler circuit again. because this graph is connected and also still even. So we can build another Euler circuit. And then we combine these two Euler circuits to get the green one. Make sense? Okay. Yeah. So this is the general idea. In detail, you can read in the textbook. Okay. So this proves that if you have an even degree of vertexes for all vertexes, then you can find the Euler circuit. Okay. Okay. One application. Okay. No application. Yeah. One example to demonstrate this proof is this one. Okay. So how on earth you can show that this contains an Euler circuit? Okay. So in first sight, how to draw it? So one way to do this is you can form actually two Euler circuit here. Okay. So you can form this Euler circuit like this first, and then wait, this, 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 and then come back. Okay. And then the other one is going the other way. So let me put this direction in. And then the other one going from where? Going from here and then come here. And then come here and come here. Okay. Maybe this one is not readable. Okay. Which one better? Okay. Yeah. So you can first form these two Euler circuit and then you can try join them at the edge. At the point. Okay. And then this one is called the Muhammad Shimitas. Okay. So Shimitas is the two knife. It's like a two knife here. Two sword. Okay, so let's go back to the bridge. The bridge question. So we have the bridge, something like this, connecting uh, four parts of the land, and then we got two coming like this, four, and then one, and then so seven bridge. So this is the seven bridge. Yes. Oh, if I don't spell the name on the bridge. Okay. So how to turn this into the graph problems? So we can also use the connected component idea here. So you can imagine that this land here, okay, they are connected. Okay. So you can draw some dual graph. Okay, let me do. Okay. So you make the land into a dot. Okay. Contract them into a dot. So you got the A, B, C, D, which is this A, B, C, D. Okay. And then you draw the bridge as the edges. Okay. Then to answer this question, you just need to ask whether you have even degree of vertexes or not. So, do you have even degree of vertexes? So the degree of A, B, C, D are all 1. Okay. So there's no Euler path that you can draw on on this term. Okay. Is it clear? Is it clear? Is it okay? Which is odd. Okay. Let me add that. Which is okay. So by the theorem before, there's no yeah. So no Euler. No Euler circuit. Circuit by theorem. Okay. Yeah. Any question? No? Any question? No. Okay. So let's take a break for 10 minutes and then we'll come back. 5:03.啊，这个那个，老师，来看那个，老师，你的那个什么可以弄掉？这个哪个是 meeting 它这边做可以弄掉这种笔，哪个呢？换掉那个，这样，那这边，哦，我先看。哦，你都没有呢？我都有了，像你这样，我都有了，可能是我是 boss 啊。
这就是
啊，
比如说
呀，
从这儿开始，然后这样走回去，也可以叫投篮。
那也可以，但是他要比较 general 的情况嘛，对不对？
走同一个点是没有问题。就是我这儿的时候走了一回，回来
啊，对，走同一个点是下一个叫做还没有登号，
对，
呀，
就没有问题。
对，哦，OK，等一下啊，我看一下。
那是很像他们
哪个？
第一个那个关不能这样啊，但是错了。你的，我这样啊可以啊。
可以，你可以换成搞笑的。
喂，从搞笑，等我哟。
可以。
这个跟拍，让我看一看你的跟你一样的，他们差别是什么？
没有一样，没有一个是深，一个是宽，一个要停在原点，一个不用停在原点，其他东西可以。
啊，这个要听原点，一个不用。如果这个没有听原点，啊，明白。明白了。
我应该没有少个字
这当念啊，歪了。
啊，exactly one，我真的少了一个字写，有点怪怪的。什么？
这念歪了啊，
对，哦的。
我就想到 oyster，真的。
喂，这个很重要的字我竟然漏掉了，真是糟糕。
Exactly one，
这样
exactly one。
，hello hello testing everyone okay. Okay, before we continue, I should make some amendment here. So the Euler path just now, when we introduced the problem is exactly one, right? When I wrote it down, I forget to add the exactly one. Okay, otherwise it's no meaning because you can just repeat the path. Okay, if I just say contains every edge, you can just keep repeating. Okay, but exactly once you only can pass through once. Okay. So this one is very important. These two words. Uh, also, I think I realized I keep talking about simple path. I didn't give the example. I mean, I didn't give the definition. Did I give the definition or not? I think I didn't give the definition. Simple path. I keep talking about simple path just now. So what's a simple path? So what is simple path? Okay, simple path is a path with no repeated edges. Okay. So let me write down. Okay, let me write it here. So definition, what's the simple path? Simple path is a path without repeated edges. Okay, so you cannot repeat your edge. So for example, you cannot write. Okay, let me A B C, right? So you cannot do A B C B. Okay, it's not a simple path. Okay. Yeah. So yeah. Okay. I think that's all. Okay, just now we talked about how to find an Euler circuit. Okay, Euler circuit. Now we want to find Euler path. Okay, just now, one of you just now, actually it's Zhen Qian, right? Zhen Qian just draw something like this. Zhen Chang, sorry. Hey, Zhen Qian, Zhen Qian, okay. Don't cheat me. Okay, he draw something like this. It's fine. That's fine too. Okay, so you want to draw like this also can. Like squeeze also can. In fact, I think, oh, okay, never mind. This one, okay, it's not Hamilton as well. Never mind. So you can draw like this as well. As long as you touches every edge once. Okay, once. Only once. That's fine. Any pattern you want to draw, that's fine. Okay. Oh, I didn't show you the end. Okay, this one. Because I go do some not research I just search of it, search the history of the bridge, and then I found out someone gave this map here. So in the end, right, the map, the city encounter some war, so all the 7 bridges are destroyed. Okay, and then it get replaced by this T shape of a bridge. Okay, yeah, this is the end of the story. Okay, okay, we can't like this. Okay, next. Okay, so next we want how to find what's the condition to find an Euler path. So a connected multi-graph. Okay, we allow multiple edges again. Has an Euler path. Okay, but not an Euler circuit because if you got an Euler circuit, it's also an Euler path, right? Because circuit is a path. So we don't want Euler circuit, we just only want Euler path, which the starting point and ending point is different. So how to check? It exactly has the 2 vertexes of odd degree. Okay. And then you should think about which 2 vertexes are odd. Which 2? Which 2 vertexes should be odd in the Euler path? What do you think? Any idea? Any idea which 2 vertexes has odd degree in the path? Anyone got any idea? Is the starting and the ending. Okay. When you start, you got +1. When you end, you got another +1. Okay. So if you want to find the Euler path, if and only if this graph only have these 2 vertexes as odd degree. Okay. Okay. So one way is also clear. So which one is clear, easier? So if you got an Euler path, okay, the Euler path, then you get exactly 2 vertexes of odd degree. So this one is easier because okay, I just write out because the starting and ending vertexes as well. Vertexes. Okay, vertexes have odd degree where the rest have even degree, right? Because when you go into the other vertex, you have to exit. You go into, you have to exit. You go into, you have to exit. You go into, you have to exit. Go into, you have to exit. So +1, right? So +1. So only 2 vertex is you come out and then you enter. Okay. Or of course, maybe you can like pass through the starting, but when you pass through, it's like situation is the same as the other ones. You have to go in and then exit, go in, exit. Okay. Is it clear? Obvious? Okay. Okay. If it is not obvious, you should point it out. Okay. So the other one is harder. Oh, let me see. I can. Let me see. I can. Let me see if I can. Okay. This one is harder, but there's a clever way to do it. There's a clever way to prove it. Okay. It is harder, but there's a clever way to prove it. So if there are exactly two vertexes of odd degree, how can you produce this path, Euler path? Any idea? That's one clever way. I give you maybe 1 minute. See if you can think of this clever way. It's the one that we use to prove the last theorem. Any idea? Any idea? Give you 1 minute. There's a clever way to do it. Any idea? Any idea? Okay, so let's take this example. Okay, this one I put example in case this is not a general thing. This is just an example. You should use this this example to think of general problems. So since you got exactly two odd number, right? Odd degree. The other are even degree. So you can just join the two vertex and then make both of them even. So if both of them, all of them are even, then you can find one. By the previous theorem, what can you find? An Euler circuit. Okay. So consider a larger graph by adding an edge between the two vertexes of degree. Okay. Then by previous theorem, we have a Euler circuit. Okay. So this Euler circuit passes through every edges exactly once. And then what you do is just remove the extra edge. Then you will get the Euler path. Is it clear? Is that okay? If it is okay, then I don't need to write it down. Okay. So you just remove. Okay. Maybe I just put one. Then okay. Removing the extra edge will produce an Euler path. Okay. Okay. So let's try this again. So of these three, which one have the Euler path? Okay, so what do you need to do? Check the degree of the vertex. So which one has exactly two odd degree? Does G1 has two odd degree vertex or not? Who are odd in G1? D and B. Okay, so this means there is an Euler path. Okay, but there's no Euler circuit, right? Because Euler circuit need all of them even degree. Okay, how about G2? Who are odd? B is odd. Who else? And D. Okay, anything else? No. Okay, other are 4 and 2. How about G3? A, B, C, D, E, or everything? Most of the thing, right? Okay, so there's more than 2. Okay, so there's no Euler path. Is there any Euler circuit? No, right? Because there's not all of them are even degree. Okay, no Euler path or Euler circuit. Okay, so I said that these 2 points is actually the starting and the ending point of your Euler path, right? So you should be able to draw the Euler path from starting from D and then end with B, or either way. Okay, so can you do it? So from D, where can you go? Can you draw the Euler path from D? Which way do you want to go? Which way do you want to go? D, you got DA, and then only one way can go B. After B, where do you want to go? A. Cannot go A already. C, and then D, and then go back B. Okay. So yeah. How about G2? Okay, you want to start B or D? D. Okay. D, which way you want to go? DC. Okay, maybe go C first. Where you want to go? F. Okay. And then D. Okay. E. Okay. And then F, there's one way only you can go. Okay, F, only one way can go G. And then G, which way you want to go? A, and then B. Okay, one way you can go. Okay, you want to go G or C? G, and then one way is C, one way is B. Okay, you will always end with this and start with these two. Okay, wow, this part is so convoluted. And maybe, yeah. Okay, good. Next, okay, next idea is just now some of you asked me whether you can pass through the vertex once only. Okay, so just now you see we can pass through vertex, like see this one how many times? Twice. Okay, this one also twice. Okay, this one twice. So if it passed through exactly once, then we will call it a Hamilton path. So definition. A single path graph that passes through every vertex exactly once. It's called a Hamilton path. Okay. So maybe I don't write out the definition for Hamilton circuit anymore. I just say similarly for Hamilton circuit. Okay. Just make sure your endpoint and the both endpoint is the same. The starting point and the ending point. So similar for okay. So let's keep going with this. Okay, one example is this one. Okay, so this Hamilton, right? So he got a quest. So he want to go around the world of about 20 cities, okay, without revisiting the cities. Okay. You think these guys are maybe crazy? So they want to go over 20 cities, eh? They don't want to revisit the cities. So they make into this is it called dodecahedron? So there are 20 vertex here. Okay. So actually you can smash this polyhedron. You know what they mean by smash it? So smash it flat. So you got like your hand, right? You smash it flat until like this. Can you imagine that this thing is this? Can so it's like this point here, right? Is the point here. Okay. You smash it at the middle, and then you will get this graph here. So how many faces are? 1, 2, 3. Oh shit! How to count these faces? How to count it fast? Maybe can anyone count the faces here? Anyone count the faces? Huh? 12 ah? 12 ah? Okay. Okay, I'm not wrong. Okay. So make sure that here got 12. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh. Where's the 12th one? At the bottom. Okay. So the largest one is the 12th one at the back. Okay. So yeah. So one way to solve this puzzle here is the blue line. Okay. So you can go from here, 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 here. Okay. So this is the circuit. Okay. Actually, you can do it. So yeah. Okay. So this is the Hamilton path. So let's try with this three example here. See if you can find some Hamilton path or circuit. Let you try. Okay. If you got any Hamilton path or circuit, you can tell me, and we can discuss. I'll let you try for 2 minutes. Anyone got any idea? Any Euler circuit on G1? Any Euler circuit on G1? Have anyone tried out? Huh? Any Euler circuit on G1? No? No. How to prove? Hmm. This one is Hamilton, not Euler. Oh, I said Euler. Hamilton. Sorry. 1, 2, 3, 1, 2, 3. Yeah, this one no Euler path. Hamilton path. Only need to pass through vertex once. No need to pass through every edge. Okay. So any Hamilton? Huh? But huh? How? You can go from A, B, C, D, E, A. Okay? Passes through once. Okay. So how about G2? G2 cannot, right? Because can B2 have? B2 cannot have Euler circuit, but sorry, Hamilton circuit, but can have Euler path, right? Huh? A, B, C, D. Because if you want to do Euler circuit, then you need to go forward and then go back. So you definitely have to intersect, revisit the vertex again. You could have Euler again. Hamilton path, but not Hamilton circuit. Okay? Okay. For G2. Path doesn't need to have the same starting and ending. Okay. G3. How about G3? G3. G3 got no path or either path or circuit. There's none. Okay. Because you need whatever you do, you need to pass by at least twice of A, B, D, C, or E, F. You can try all the possibility. No matter how you do, you need to visit A, B, or D, C, or E, F, either one of them twice. Either path or either circuit. You can try. Okay, so I will put here now Hamilton circuit or path because any path or circuit will visit either AB, DC, or EF twice. Okay, you can try. You can try. Go and try. Okay, everything you try, you must encounter like need to come up from this single path here. Yeah. Okay. So you might wonder, is there a way to find Hamilton circuit? Okay. Is there a similar way, maybe count the degree of vertex or what? Actually, not in general. Okay. So what are the conditions for the existence of Hamilton circuit? We don't know in general. Okay, we don't know in general. Okay. For some cases, we can say yes or no. So for example, one cases is a graph with a vertex of degree 1 cannot have a Hamilton circuit. Can you think why? Can't go back. Okay. That's mean because in Hamilton circuit, each vertex is getting uglier. Is incident with two edges. Okay, right. I think this condition is same as Euler circuit, right? If Euler circuit have one vertex, you cannot go back. Can you? Can you go back or not? If one vertex. No, right? Yeah, also cannot go back. But Hamilton circuit also, yeah, cannot go back. This one is about circuit. Okay, second condition is if a vertex in the graph has a degree 2, okay? If a vertex in the graph have degree 2, then both then both edges will appear in the Hamilton circuit. Both edges must be part of the circuit because you need to enter and exit, right? So if you only have two edges that incident to the vertex, then these two must appear in the circuit. Okay. So what's the next part? No wonder it's very hard. Okay, what's the next thing? Okay, the next thing is when you try to construct the Hamilton circuit, okay, if the point has more than two vertex, two edges, then you can simply remove the edges because you won't use those edges again. Because you only passes through the vertex once. Okay. So when a Hamilton circuit being constructed, passing through a vertex, then all remaining edges incident with this vertex can be removed from consideration. Okay, so maybe if you can't picture this, maybe I use this example. So when you construct this Hamilton circuit, right? Okay, you walk this way. So this edges actually you can throw it away already because you won't use it again. If you use it again, then you need to pass by B again. Okay, so that's mean once you use once you pick the path, then all the other edges you can just the remaining edges you can just you don't need to consider anymore. You won't use it again. You won't come back to this edge again because if you come back, then you need to meet the B again, which is not Hamilton. Okay, this is what you want to do. Okay, so example of two graph that doesn't have a Hamilton circuit because G got a vertex one, vertex one, vertex of degree one. And then this one, how about this one? This one, why? Why is it? Remember, why is it? Why is it this one doesn't have a why? So why is it? Hmm? So this one is degree 2, this one degree 2, this one degree 2, this one degree 2. Okay. But this one only degree 4. Right. So why? Let you think about for a while. Why this one doesn't have one? Huh? So for Hamilton circuit to exist, right? All these edges has to appear. Okay. But but once you use this, then you will pass by C once, right? And then you use it again, you will pass by C twice. Can you see it? Can you see it? Okay. Huh? Yeah, cannot pass by C twice. So I mean, yeah. So to form the Hamilton circuit, to pass by A, B, C, D, E, right? Because these are all degree 2. So you must use up all these edges, okay, to pass by just A, B, D, E. Okay. But when you use up all these path, right, you must pass by C twice, no matter how you choose. Okay. Can follow? Can follow no? Can. If not, just raise your hand. Okay, if not, just raise your hand. Is there anyone speaking in the team? Let me check. Jingrui here. Is Jingrui here? Jingrui. Oh, you asked me what attendance? Is it for last week one? Not last week. Oh, let me later I have a look. The week before? Okay, let me have a look. Okay. Okay, so this is the Hamilton business. So okay. So let me just put a remark here for all the that for all the circuits, sorry, for all the circuit that passes A, B, D, E once has order. It has to pass C twice. Okay. And then this one is E is the degree 1 to X. Okay. Okay, good. Okay, some example that we encounter is this complete graph or the cycle. All this got the Hamilton path, right? You just pick the outermost one is the easiest one. Or you can pick the harder one. For example, this one, the star. Star. Yeah, star. Star. Nothing so. Why don't move? Start again. Sorry, I think the line got problem. Let me try again. Okay. Sorry, you didn't tell me this one screen becomes smaller. Yeah. Okay. Just realized. Okay. So yeah. So there are few Hamilton path you can consider here. So for example, this one. So you can consider the outer one, okay, the usual one. Or you can consider the stars. Also can. Okay. Yeah, both can. This one maybe like this. Okay. Yeah. There are few ways to do it. Okay, this one cannot. This one. Okay. Yeah. And then cycle is easier, so just like this. Okay, what's next? Okay, next. Hopefully we can get to planar graph today. So next, what do we have? Should I introduce this? Okay, maybe we just introduce. We won't talk about the proof. The proof maybe hard, so no need to talk about. So, another way to see whether you have a Hamilton circuit or not is you can check on the degree, but a bit hard to check. This one you need to check for every pairwise, every pair. So suppose you got a simple graph. Starting with vertex greater than 3. Smaller one, we cannot form a circuit. So need to be at least 3. So if all the pairs have degree, the addition of degree greater or equal to n, okay, for every pair of non-adjacent one, you cannot pick the one that are connected by that is incident to the same edge. Then U and V, then the G is G has a then G has a Hamilton Okay. More calculation you need to do this one. And then this one will give one easier checking called the Dirac theorem, which is the corollary of this. So this one, what you need to check? You start with the same condition on the graph. Okay. So at least 3, because less than 2, can you form a... Yeah, you cannot. Can you form? Less than 2 you can, but our case is a simple graph, so we don't allow multiple edges. So such that the degree of this one is easier to check. So you need to check the degree of every vertex, which is at least n/2. Okay, then you can find a Hamilton circuit. So that means it's like you give yourself enough room to avoid the revisiting. Okay? You give yourself enough room. Yeah. Okay. Yeah. So how enough is it? n/2. At least n/2. That would be good. Okay. So if you note that, if I can, how to say? Yeah. Okay. So these are the two way you can check. But you can note that the converse is not true. Okay, converse is not true for all. So you cannot say that if I have a Hamilton circuit, then we have a sum of degree is greater than equal to n. Okay. So a quick example is this one. So the converse of so my statement is the converse of Gauss theorem is not true. Okay. So this means even though you got a Hamilton circuit, there would have 2 degrees that add up less than n. Okay. So how on earth you gonna prove this? So you just get a counterexample. So this one is the not K5, C5 cycle. But you can see that. So you just pick any 2 of them. Degree U plus degree V is equal to 4, but it's less than, what is the n? N is the vertexes, which is 5. Okay. But the Hamilton circuit is this one. Okay. So you got a Hamilton circuit, but the sum of degree is less than 5. Okay. Any one you pick, 1, 2, 3, 4. It's symmetry. Doesn't care which one you pick. U and N. Okay, should we go into planar graph? You want to go into planar graph? I think we should. Do you want to go into planar graph? If we go into planar graph, let me do one interesting, show you one interesting formula, and then we will stop there. Is it okay? Okay. Okay, give me 10 more minutes. Okay, next part, we talk about planar graph. Okay, I know you like to ask about application, right? Or your textbook give one application. So let's say, what's planar graph about? So you got house, okay? You got different utilities. When you make the line or the cable, you can't have the tube intersect with the electricity, right? You can't have the pipe intersect with the electric cable, right? Okay. So you want to consider the graph that have no intersection of edges. Okay. So you don't want this to happen. Of course, in 3D, you can leave it up, right? So in 3D, even though you got intersection, you can just bring it away. Okay. So sorry. So So that's why we call this a planar graph. Okay, so it works on plane. Okay, so what's the definition of planar graph? Okay, so okay, let's introduce this definition and then we will stop at one interesting theorem or formula and then go for the day. Then going to theorem. So a graph is called planar. Okay, we want it to work on 2D. So it's called planar if it can be drawn in the plane. Okay, in the plane meaning the 2D plane, not the airplane. Without any edges crossing. So such drawing will call it a planar representation. Yeah, representation. It's called planar representation. Okay. So let me ask you. Let me ask you. Is this graph here the I think it's called a K4 graph, the complete graph for n equal to 4? Okay, so you join all the vertex together. Is this planar? Huh? No? So you'll get fooled by this representation here. Okay. so so you can what you can do is you can pull this graph up, pull this edge up. Okay, so bring it up. I can bring it up. You learned isomorphism last time, right? Okay, so you can bring this up. So these two graphs are isomorphic. Okay, so they are connected before, they're still connected after. So you can try to bring this up. Okay, such that they are not intersect. So this is the planar representation. This is the planar representation of. Okay. Yeah. So if you cannot do this, then it is not planar. So can I have this example here? So this is a cube. Okay. It's the same idea as before. You flatten it on one side. Okay, you will get this. Okay, so you flatten it, and then you get this picture here. So on here you can see that they intersect, right? You see, intersect or not? Right? Then the edges intersected. Okay, but if you draw it like this, it is not intersecting. Okay, so there's no intersection here. Okay, so can you imagine this to this? So you like punch here, punch to flat, punch it to flat. Okay, and can understand what's punch, right? Okay, like the tin, you after you drink, you squeeze it. Okay, one thing that is not planar is this one. Okay, so this one is not planar. K33, the complete bipartite graph. So how to draw this? Did I draw this anyway? Maybe let me redraw this. So let us draw this bipartite graph. So you need to join each one to everyone. Join one to everyone. This one is big. Bipartite. Okay. Okay, this one is not planar. Okay, so my way of thinking it, you can compare it to the textbook one, but my way to thinking it is you can take this, okay, take this vertex, move it down. Okay, can you imagine it? So take this vertex and bring it down. Can you imagine? I'll draw it up. You can in the meantime you can try and imagine it. So I take that vertex and then I bring it down. This one will like reduce a lot of intersection, right? Okay, so I bring it down. Okay, I bring it down. Okay, I bring it down like this. Agree? Is everyone agree? You will get this. Okay, you take this and then you bring it up. Everyone agree? Agree you got this? Okay, happy? Okay. So now you're left with this three line here. Okay. So how many places this this dot can go? So either it can stay outside here, okay, or either it can go into this region here, or either it can go into this region here. Okay. So my argument is no matter which region you go, there will be non-empty intersection. Okay. So if it stay outside this region here, you see here already start intersecting. Similarly, here, you can try. Okay. How about inside here? Okay, inside here I can draw for you. So you get like this, like this, and like this. I think this is the minimal intersection you can get. But you still will have one intersection here. Right? Agree? Okay. So similarly, if you move this to this side, you will still have intersection. Okay. So you cannot avoid. Oh, so there's no answer. Okay, let me write this one, call it V. They are, okay, let me label the region R1, R2, R3. There are three region R1, R2, R3 to place the vertex V, but none of them can avoid 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 H H crossing. Okay, just now we use H crossing, right? H crossing. Okay. Okay. Any question? I think it should be clear from the picture. If you don't see it, you should raise your problem. Okay. Any question? Any question? No? Okay, give me 5 more minutes. I want to finish this formula. Okay, this formula is very close to my research. I mean, as close as possible from your syllabus. Okay, this one is very interesting. So, what's the theorem here? So this one is called Euler formula. Okay. So let G be a connected planar simple graph. Okay, so you start with a planar simple graph. So there's no edge crossing. With a EH just and V vertexes. Okay. Then let R be the number of region. Just now I show you the region, right? And representation. G. Then R equals to E minus V plus 2. Okay. Okay, I want you to believe it first. So I give you example. So let's try this. Okay, this square here. So this is a planar representation. Okay. So following the rules here. So got 4 edges. E equals to 4. V equals to 4. Okay. So how many region you got? One is inside, one is outside. Okay. So R equal to 2. So 2 is equal to 4 minus 4 plus 2. Okay. So maybe you think this one is easy, okay? So maybe we draw something Other. Maybe like this. This one planar, right? Okay. You want complicated a bit? Oh, more complicated? Or maybe like this. Okay, enough, huh? Okay. Okay. So let us count how many regions. R1, R2, R3, R4, R5, R6, R7. Okay, outside. Okay. And then how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay. So 10 edges. How many vertex? 1, 2, 3, 4, 5. 5. So is it 7 equals to 10 minus 5 plus 2? Okay. Yeah. Okay. Yes. So what's going on? So what's going on here? Okay. So this number here, right? Actually, we call it Euler characteristic of this simple graph. Okay. So maybe I write the special name. This two I have to give special name, right? Because this two come out of nowhere one. So Euler characteristic of planar graph. Euler characteristic. In fact, this Euler characteristic, right? You can assign it to any surface or any object, any surface. Okay. Like for example, cube, you also can assign Euler characteristic. So it turns out that if you assign this Euler characteristic Euler characteristic to of a polyhedron, complex polyhedron, it's also always true. Okay. Complex polyhedron is what? It's like a cube. Okay. And the dotted cahedron you saw just now, the voyage problem. Okay. And then also the pyramid. Pyramid is also so if there's a number assigned to this, it's also 2. Okay. Actually, they are the same as sphere. Okay. So Euler characteristic of a sphere is also 2. Okay. So these are the same thing. So if you look at this, right? If you remove the edges, remove the vertex, I mean you like how to say how to say like the edges is very sharp. So what do you do? Like how you like you how to call it? How to call it? You what? You how to say How to say? Also Chinese is like 磨平啊. Huh? How? 讲讲 How to say? How do you call it? Like you curve it cannot have very weird. Huh? Remove the sharp. You remove so you remove the corner. So you make the corner blunt. Okay. Then it's actually a sphere. Can you imagine? Can you imagine? Okay, good. So actually, right. So actually, this number is very interesting. So the surface in the world, right, split into 3 cases. So one is 0. So EC can be 0 or greater than 0 or less than 0. Okay. So in this world only split into these 3 characteristic or the characteristic. Either greater than 0 or less than 0. Okay. Yeah. I mean in this world, all the surface split into these 3 cases. What I mean, wait, I mean, okay, maybe you think of it like a number, right? But this is some result on the surface, okay? Where we call this one flat, this one spherical, and then this one hyperbolic. So your planar graph stay in this world. So planar graph. Okay. Yeah. So these three surface coexist in universe. Yeah. What? Show you what? What do you mean? Oh, I mean, okay, okay. I mean, surface, just now your planar graph is like, okay, so spherical is something like this. So, I mean, this one is just extra knowledge, not tested in the, but I will show you this. So how to draw this hyperbolic surface. Something like this. I think so. I don't know how to draw this. Maybe like this. Let me try. Okay. I don't know whether I can do it. So this one have to like go downward. How to draw downward? Okay, I don't know how to draw this hyperbolic stuff. So it's like something like this going down. Yeah. Okay. It's like a saddle. Saddle. Don't know how to draw. Something like a saddle. Okay. But yeah. But on the earth, right? You can see it is flat, but it's actually spherical. So you are working on the small patches here. So you think that it's flat. Yeah. Okay. We call it a flat Euclidean space, but anyway, never mind. Okay. So black hole is something like this. Okay. Yeah, that's all. I mean, we haven't proved it. We will visit the proof. But I want to tell you this 2 is a special number here. That's all I want to say. Okay. This 2 is a special thing for the planar graph. Okay, any question? Or you want to know about black hole? I'm just kidding. Just kidding. Okay. Yeah, I mean this everything in blue is just extra, but what I want to impress you is this number 2 here. This number 2 is a special thing for your piano. Okay, that's all. Any question or not? We didn't prove this. Maybe if possible, we will come back to this proof next week. Planar graph and then coloring and then that's all. Okay. Any other question? No? If not, we can start doing the tutorial question. I'm sure that you can't finish this week tutorial question either because I put a lot of question inside because I think you need to practice. I also put some, there's one interesting proof question we can discuss later. And others we can also discuss on how to find the it's actually on tested last week material, so we can discuss as well if on request or either I find it interesting. If not, let's break until 6:13 and then we will resume. 太感冒了。他感冒要不要冷气关小一点啊？关掉了。好，那开门呢？哎，喂，好，拜拜，加油。呀，来，我朋友的，
什么意思？对，我也要问这个。
这个就是这个号码的意义，这个号码的一个名称吧。要怎么找啊？对，要怎么找是另外一个。
我就听他怎样找
是2的名称
啊？
是这个是来解释2吗？
对，这个2有特别的意义，这个2有特别意义。如果如果你的surface 是可以这样子画呢，你就可以这么找，用这个 r 减掉 1
加 v
加 v，r 就是它，其实这个 r 不是面，就是 faces，
就是它的线来创造出来的面。
yes， 对，没有错，没错，yes， 对，就是你可以有些surface 啊，比如说这里圆圈啊，比如说刚才那
圆
里
圈是属于一条线吧？
OK，不是圆圈，我们要看叫什么啊叫什么啊就是忘记了，不好意思，sphere 叫什么啊圆
是什么？
也不是圆锥，
椭圆。
椭圆。OK， 没有椭圆啊，就真的圆啊，我只是画到就有点椭圆吧。所以你看这个圆不是，你可以用三角形去 partition 它。
对啊。
OK， 然后你如果用这个东西去算的话，你可以算到
这个是立体的吗？
立体啊，
那里边三角形是
就是它表面。对，你把它表面
无限分割成三角形。
yes， 没有无限啊，因为你这个东西是一个有限的嘛，所以你肯定是有限的。然后你再用这一个去算它的话，不是那具体来说，刚好不能跟你讲讲整个具体。
单纯想问一下这个单词的意思。
这单词意思啊，这单词只是说一个特性可以都可以。
这个
polyhedron 是这种形状，就是 cube 啊，或者用三角形组成的 pyramid 啊，或者那个五角形啊，
你可以用这个五角形做那个，你能够贴成那个立体，可以想这样，这样，然后你就应该要贴，然后
就跟那个
哪一个
有一个化学就是碳60，就是用五角形和六角形拼出来的一个球体。
也差不多类型，下节课这节课做 tutorial，
是不
讨论 tutorial
不一定是2的，好像也有说3或0
对，也有其他
就可能有其他的，
也有其他情况，
怎样的情况？
但是放上面怎样的情况？没有放哦，
怎么这样子往回啊
Hello，哎，你们怎么走了走了
想问啊，很多人回去啊，因为看到我们回去了因为他们看到我们回去
要回去了？怎么？
哎呀，回去上网课，
回去上网课？什么叫回去上网课？
就是回宿舍在上
啊？哦，OK，怎么？这样？怎么？他问你可以先问。下周，因为他们今晚考试，他们今晚有那个replacement，还有3个有些中那个统计，对，
所以下周
下周
对下周
对，本来是想今天先，但是昨天没考到，是因为昨天本来我们估计要考，但是昨天没考到，所以今天才考，所以就是那个 replacement，所以就等他们这样。Hello，OK
你要讨论了
差不多。Hey, you guys want to discuss straight away, or you guys want to? The reason I don't want to discuss straight away is I don't want to like straight away expose you the answer. I want you to try first. Yeah. I'll discuss at 6:25, okay? 6:25 discuss. Today I got quite a lot of questions. 6:25 discuss. So you can pick any one of it, you can vote on it, vote on it. And then 6:25 we will discuss. You just pick any one you can vote on it, then we will discuss 6:25. Because this week quite a lot of questions. And I purposely put 9.6.44 in so that you got practice. Okay. So make sure you know how to do 9.6.44. Okay. Okay. Not just doing on your own. I don't want to straight away give you answer because I don't want you to like just study the answer. Okay.
这个老师其实还有不一定是这个数字对吧
depend on 你的设备。depend on 你要看的。
那是没有例子，我忘了。
这样子在我脑里没有我脑里没有
对啊，是可以问你上个星期的这个问题。
可以，你讲啊。
看到这个了。
我不知道有没有哦，看一下啊。2减2G，这个应该拿不到1。这个2.2G 是看你的surface有几粒洞。如果你有 G 个洞的话，你就减掉2乘那个 number of 洞。 哦，有啊。哎，真的。
anything to point 因为我常见都是2来的，
哪里？常见普通啊。
都是
有一吗？哦，这是历史什么？谁是一？triangle，说 triangle 是一吗？triangle 是一，所以是非是，
感觉这个
什么？
有点可能离Seng很远很远，
对啊，离很远很远啊。I mean，它这个只是一个，
很抽象。
对，
没事啊，
没
没事啊，我
OK，
就问你，
呀，正经，来。Yeah, just now the student left the class because they are SWE, so they still got Thursday class, so they left the tutorial. And then some of them say they want to leave because they get wet, so I let them leave. Yeah. So yeah.
NT 型嘛，是应该是我可以理解是这样嘛，就是我就是 assume y 是等于2啦，就是当它 x 等于1，那就是1 2，然后它的把例就2 1。
Okay. Yeah. So, you didn't open your mic. Yeah. Someone muted me. Okay. Yeah. So I mean, because depend on the groups, maybe the way of their thinking is similar. So if either one of you can ask some question, then it will help a lot of people. Okay. Even a stupid one will do. So make sure you guys ask question. Otherwise, we will be like disconnected. You know. Yeah. I will disconnect from you guys. So we are too connected. Connected. Okay. Anyways. Okay. So let's come back to this week tutorial question. This week is what? This week is this week a lot because there are a lot of short questions, which I think is quite good for you to attend. Okay, 9.6.44, they give you a pole set and then ask you whether it's a lattice or not. Okay. So you just draw the pole set. Okay, so let's say you got this pole set, and then yeah. So in the first pole set, give you a pole set. Can you notice whether this is a lattice or not? Lattice is every 2 points, you need to have a greatest lower bound and a greatest lower bound and a least upper bound. Okay. So is it true for this one? You got like different branch. I mean, you can just compare these two, right? Okay. You also can compare these two. Okay. Yeah. If you connect these two, there's no upper bound. So there's no greatest, lowest upper bound. Okay. 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 Hopefully you don't forget the definition. And then B, if you select any two, okay, so the upper bound will be on the line as well. So if you select 25 and 5, the upper bound is 25 and 125. And then the lowest upper bound is 25. If you look at least upper bound for 5 and 25. Similarly, you can do for all the other. Okay. So, yeah. Okay. So another question is whether these two pole set are lattice or not. Okay. So meaning give me every two elements, you need to produce me a greatest upper bound and lowest upper bound. And the answer is yes. Okay. The answer is yes. So I give the reason here. Maybe if you don't do it, you won't know what is this answer talking about. You need to try first. Okay. Try. How to try? So one way to try is first you draw this draw this pole set up first. So what is z greater or equal means? So this means AB is in the pole set if and only if A greater than B. Greater or equal. Okay. So this means, for example, 2, 1, right? So 2 is related to B, so like this. And then 3 like this. Okay. So you can see that this is a bit different from the what? From the usual order. Usually we look at z less than equal to, but this one they turn the direction, turn the direction. Okay, so this means the direction change. Okay, yeah. The answer is yes. I already produced the solution, but if you don't do it, I think you can't see why is that the solution. But one thing to note here is the direction change from the usual concept. Okay, once you change the direction, then the greatest and lowest bound change. Okay, because your order changed, right? Right? Because your order changed. Okay, because partial order has direction, keep going up one. So the convention is we look from bottom to up. So if they are related, we will draw upward arrow, and then we will remove the arrow. Right? Remember the Hessel diagram? Hessel diagram. After we got this arrow, then we will remove the arrows. Okay? Yeah. Similarly for this one. Okay? Also change the direction. So the order changed. That's why you will see something weird happening. Something odd happening. Try it first. If you don't get it, bring it next week. Okay. 10.1.2, 1.4, 1.8. Just try it first and then we will see. 10.1.12 actually how to say, not hard, okay, but it's relating graph with relation. Okay? So this one is a relate graph and relation. Okay. So whenever there's a loop or edge, we will say that they have relation to each other. Okay. So sometimes relation can use graph to model. Okay. Okay. This one is one I want to discuss about. 10.2.18. What is 10.2? Okay, 10.2.18. It's 10.2. Okay, 10.2.18. Show that in a simple graph with at least two vertices, there must be two vertices that have the same degree. Okay. So is this something? I'll say. So you go to simple graph. Okay. If there are at least two vertex, there must be two vertices that have the same degree. So how on earth you gonna prove this? Let me write down the question. So in a simple graph with at least two vertices, they must be two vertices that have the same degree. I think this one is a strong claim. Okay? Quite a strong claim. So whenever you start with any simple graph, right? Okay, no multiple edges. At least two vertex inside there. Okay, at least two. There must be two vertexes that have the same degree. Okay. I think it's quite a strong claim. So how on earth you gonna prove this? So this proof, I think, uses the power from previous chapter, okay, from the counting. We can use the pigeonhole. Okay, so how to use pigeonhole? So suppose you look at one vertex, okay, just stand on one vertex, and then how many degree you can have? You have, suppose you have n degree, n altogether you have n vertexes, okay. So at most you can have n minus 1 degree if you connect to all of them, right? Either you don't connect to them, or you connect of them, connect two of them, connect three of them, connect. Most you can get is n minus 1. Okay. But in this case, you got n vertexes and n holes, pigeonholes. So you cannot use pigeonhole yet. But it cannot be the case that the degree of x is both n minus 1 and 0. Right? Because if your vertex connects to all of the vertex, this means all the other vertex has at least 1 degree. Right? So 0 and n minus 1 cannot coexist. Okay. Can get it or not? Get it? Can get it or not? You want me to draw? Okay, I draw. So, for example, n equals to 4, right? Okay. So how many possibilities? Okay, this one maybe call your x. I think the possibility is, okay, so maybe smaller, precise. You can use this and then think of a larger example. Okay. So what you can do is either you are not connected, either you connect to one of them, either you connect to 3 of them, either you connect, 2 of them and then 3 of them. Okay, n minus 1. So it's like 0, 1, 2, ... up to n minus 1. Okay, so if n minus 1 happens, okay, degree of all the vertex, degree of v for all v, vertex v is greater or equal to 1. Okay, so that means this n number cannot coexist. If degree 0 happens, okay, then none of them can connect to n minus 1 of them. Okay, so that means there's only n minus 1 hole actually. Okay, then you can use pigeonhole. So pigeonhole say that if you got n minus 1 objects and n pigeons, if you got n pigeons and n minus 1 pigeonhole, then 2 of them must be in the same pigeonhole, which means 2 of them must have the same degree. And then this one, right, can apply into your party. So what do I mean by that? So in a party, so if you are if you know one person, you can draw one edge. Okay. And then this graph is a simple graph, right? Because if you know him, he know you. I mean, assume it's symmetry. Okay. Then if there are more than 2 persons go to the party, there must be exactly 2 persons who know the same number of friends inside the party. How? Exactly 2. Exactly 2. Oh, I mean, at least 2. At least, I think at least 2. 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 You can find at least 2. Pigeonhole maybe can have more n goes to. Yeah. At least 2. At least 2. Okay. Not exactly 2. Yeah, I think it's at least. I think should be at least. Must be at least. Not exactly, but at least I think, yeah. Because pigeonhole doesn't say that only two can go into the same hole. Yeah. Okay. Yeah. At least two must know the same number of friends inside the party. I mean, if the relationship is mutual, so I know you, you know him. Okay? Yeah. I don't know, but I feel this one is quite interesting. Yeah. Okay. Okay. Yeah. That's all I want to say about this question here. Anything want to follow up?
N-1.
What do you mean?
And it's 2, right?
So
the N-1 is equal to N-2.
What do you mean by n-1 is 2? Say again. Yeah, what do you want to say? Okay.
N-1 is equal to Let's go at least 2, right?
What do you mean by at least 2? No, I mean at least two have the same degree. Vertex has the same degree. So now you need to set your degree as the pigeon's holes and then set your vertex as the pigeon. So you need to create a condition where the pigeon is more than the hole. Okay. So your vertex is n. So you need to make sure your pigeonhole is n less than n. In this case, we say it's n minus 1. N minus 1 is not this n minus 1. Is this is you count this 1, 2, 3. Maybe this one got a 2. And then up to n. This one is the n pigeonhole where I'm referring about. N choices. Okay. Yeah. Okay, yeah. Yeah. Yeah, for the rest, you can try first and then we can discuss again next week. So next week, hopefully we can discuss about the midterm and hopefully maybe quizzes as well. Okay. Okay, see you next week.
零一二它有 zero one two
Yeah.
what is 0 1 2
Hey, just now I got explained it. Yeah. So because the relation of okay, so this relation is when they have the same cardinality, they are related. So who have the same cardinality with this guy?
what is
Cardinality of the set is the number of elements in the set.
6
Three.
3
Three. So every set with 3 elements is in the equivalent class of this. Yeah, 在这边。
what is
Yeah.
那
Replacement.
那 integer 的
integer 的 equivalent class 我们没有教，所以我只是放在这里，我只是放一个 extra 吧，就是一个额外的提示吧，因为我们没有教，但是刚好这个题目说到我就写了一些东西，就 integer integer 的 cardinality 我们叫做 countable。integer 的 cardinality 叫 countable， 为什么？因为我们可以
为什么是 countable？
对，所以这个 countable 的意思是说，它不是 finite，countable 不是 finite，countable 是 infinite，但是呢，我们可以 list them in order，就是我们可以写 A1、A2、A3 这样排列出来。能够排的东西是 integer、rational 和 natural number。
所以
Yeah
cardinality 基数的话，就是它的那个
number
就是它的数名，就是一个集合里面的数。
对，没错。
这个是有3个数，
对，
所以只要是集合里面有3个元素，都有它的等价的。
yes。OK，thank you，thank you 漳州 ，and thank you 文慧，拜拜。我还没有决定我可能也来不及出还不知道，怎么嘞？